Okay, so here we count geometric objects, and in particular, in Hurwitz's theory, we want to count covers of Riemann surfaces by other Riemann surfaces. That's what we want to do. So then we'll have to decide how picky we are, and then also we'll have to define their weights. Cool. But let me also say a little bit more about why these Hurwitz numbers are interesting. So for me, the picture is the following. This is what I will call mathematical physics, and then there is some algebraic geometry here. And this is, okay, let me call it maybe string theory. I know some people will not be happy with this, but this is how I think about it. And for me, Hurwitz numbers are really an example of interactions between these three things. What do I mean by that? I mean the following. So first of all, you have some numbers. So you want to count covers, and then you need to define properly what do you mean by this count. Well, suppose you have defined it, and you have some numbers that we'll call age, and they will depend on several parameters, right? And I claim that these numbers eventually will be in Q. Well, actually, it makes a lot of sense because I'm counting something. I have to define a count that is finite, and I'm also dividing by the number of automorphism, which is finite. So it's very natural that I'm getting something rational. So here you'll have a lot of parameters. So in mathematical physics, what I mean here is that if you define your partition function, z, you define it as exponent of sum, and you have the big sum over, say, I don't want to state exactly what it is, but it doesn't really matter. And you put your age here, and you have this age that depends on many parameters, mu1, mu(n). It doesn't matter. Here you have a lot of formal variables. You build this thing, and it turns out that this thing satisfies some integrability. This is why it's interesting. So it actually satisfies what people call KP integrability. So you can think of it as an infinite list of PDEs in infinitely many variables. Infinitely many PDEs in infinitely many variables.
It's tau function.
Yeah, exactly. So the partition function is the tau function of Kp. This is why it is interesting from the point of view of integrable hierarchies. From the point of view of algebraic geometry, instead it is interesting because these numbers h that depend on several parameters are equal to the integral over the moduli space of curves. So let me put some actual g and then nu. And here you'll have some class. And here you'll have some prefactor. It doesn't matter. I don't want to write the details because that's exactly the opposite of what I'm saying. I want to say that there is a formula that states that some Hurwitz numbers they have a cohomological representation over the moduli space of curves. So this guy, I want to think of it as the moduli space of curves. And you have some genus G and some mark points N, so P1, Pn. And it's already beautiful that such formula exists. This is what some people call ELSV formula. That stands for the 4 people who came up with it in '99. So what I'm saying is that you count some objects, and then it turns out that they have a cohomological representation on the moduli space of curves. Now, this is a non-trivial statement. You might think, oh, but this is very natural, right? Because in the first place, I was counting surfaces. So the fact that I end up on the moduli space of curves is not such a surprise. But in fact, this class is interesting, and I mean, there's something interesting in the cohomology that is happening. So these Hurwitz numbers, they have a cohomological representation, and also they have integrability. And also they arise from string theory. So if you have, you take C3, then you have a mirror, you have the topological vertex, whatever it is, and then you want this to be framed, as in there is an extra parameter. And when you send this frame to infinity, so the frame, whatever it is, goes to infinity, then there was a conjecture by Marcos Marinho and Vincent Bouchard that says that if you do that, you find Hurwitz numbers. This was, let me write it here, Bouchard Marinho conjecture. And this is a theorem now by Enard, Moulasse, and Safnouk. And to be fair, there's also another paper by the same authors, Gaëtan Borot, where they describe the matrix model of these Hurwitz numbers. Yeah, so for me, this is surprising, right? That Hurwitz numbers play such a nice role in 3 different fields. And this is just one instance of that. And we have many other, we are aware of many other enumerative problems that also have this interaction. So what I mean is that their partition function is a tau function of something. Maybe it's not Kp, maybe it's KdV. Maybe it's 2D Toda, maybe it's ELW. It doesn't matter. They have a cohomological representation, and they arise from string theory in some way. And they might have a matrix model. And they all, like, so for me, this is sort of a triangle like that of interaction between these 3 things. And what is magical about in relation with topological recursion is that many of the examples that have this interaction, they actually satisfy TR. In the sense that they are generated by topological recursion. And then you might try to take topological recursion and try to understand it directly, how this works. Like, is it true that every time that I have an enumerative problem that satisfies topological recursion, then it will satisfy this triangle for some, like, you have to make sense of that every time, right? But in some sense. And we know some parts of this, but the general picture is not understood yet. We know, for example, that every time it satisfies topological recursion, then we have that. Then we have a cohomological representation. This is known. But for example, understanding when a problem satisfies TR, understanding exactly which type of integrability it has. I mean, there is the work of Bertrand, and many results are known, but it's not completely understood. So there are many nice things still to discover, but my motivation for Hurwitz theory is that Hurwitz numbers are not particularly difficult, and they are one of the best playgrounds that I know, sandboxes to play with this interaction. OK, let me erase everything. There is an extra parameter that people call f. It's referred to as a frame. And then the conjecture is that when this parameter, in the limit of this parameter that goes to infinity, you will find some numbers. And the conjecture is that these numbers are Hurwitz numbers. And now this is proved.
I think I'm asking something much simpler, like what kind of object is that map, or what is the codomain? I'm not sure.
Oh, this map. Oh, this mirror symmetry. Sorry? Okay.
I have an official question. So when you were describing this, interaction between math physics, algebraic geometry, and string theory, I was thinking the first time I saw this was many, many years ago when Dubrovin was teaching about Frobenius manifolds. Yet, every time I come to some topological recursion seminar or something, this is kind of not mentioned. Right. Can you comment on why, or maybe, is there something we don't understand yet there, or is it a political question? Then you can forget.
I would say that in my understanding, there are at least two big works of Dubrovin that are at the basis of this. The first one is Frobenius manifolds, of course, because
I'm not criticizing
no.
for not quoting, just asking, if it plays a role in the evolution of this later. So somehow, yes, those were like pillars from which you started, but I'm trying to understand, is the structure still there? Is it still
Yes. Yes. I would say so I didn't mention it because it would have been too long, but in what was written here, the cohomological class, this class we integrate over the moduli space of curves. It's not any class. Usually, so let's simplify a little bit. We are dealing with spectral curves with simple ramification points and not irregular or any weird thing. And then we know that there is a recipe to construct a cohomological class from the spectral curve directly. There is a computation that has to be done. You have to take these Laplace transforms. Sometimes it's not easy to perform them, but the recipe is there. And so when you do that, you don't find any class, but you find a cohomological field theory. So a class that behaves nicely with respect to natural maps on the moduli space of curves. For example, if you have two components, you attach them. Or if you have one component with two mark points, you attach them. Or if you forget one mark points, these are the three natural maps on the moduli space of curves. And these classes, they are not just one class, but they are a collection of classes for all G and N, and they are given simultaneously. And they all behave nicely with respect to these maps. And the data of this cohomological field theory is sort of equivalent, because of given Tal-Telemann, to Frobenius manifolds. The work of Dubrovin is intrinsically there. So it's always it's a different language to basically to do the same thing. Yeah. Also, for example, Dubrovin superpotential was used to construct spectral curves.
Make a very short comment, but I discussed many times with Boris Dubrovin about that, and we said it would be very useful to write a dictionary, but this has not been done yet. Okay.
I mean, the book of Kontsevich-Mannion, right? The book of Kontsevich-Mannion is a little bit giving this translation, in my understanding. Okay, so this was the motivation. I hope now you're all hyped about Hurwitz numbers. I didn't mention applications to Gromov-Witten theory. So if some of you is passionate about Gromov-Witten theory, there are many things there. It is involved, so these Hurwitz numbers, they play a role in the Gromov-Witten theory of P1, equivalent P1, but also of K-layer surfaces and other things. But now let's start the actual thing. So because a topological recursion is about compute, I thought that the goal of this course was, this mini course, was to be able to compute something. So this is. So here I will write algebraic geometry. And here let me write algebraic manipulations, even if it's not a correct term. And here I would say by hand. And here I would say computer. Is it readable?
Yes.
Okay. And so somehow I want to make a map of tools that you have available to compute Hurwitz numbers. So for example, here, we can use combinatorics to compute Hurwitz numbers. We can also use the group algebra. We can use characters. We can use cut and join, recursion. We can use TR, of course, by hand. I wouldn't advise that, but maybe just for the very few omega GNs you want to try. The curve is not as nice as the Miyazakani one, for example, if you start computing Hurwitz numbers by hand. But still, it's doable. It's doable. So a computer, we have several softwares. One that we put on the Slack is this Mathematica. Implemented software for topological recursion that is from Alessandro Giacchetto and is initially based on the software of, sorry, why am I saying software? The code of Vincent Bouchard. So if you don't have Mathematica, you don't want to pay for it, you can still have the 15 free days just to try for this conference, so you don't need to get a license. And maybe also other codes, if somebody wants to share. I know Paolo has one, Vincent has one. So if you feel like sharing with others your code, you can just upload it on the Google Drive. And then here from the algebraic geometry point of view, so for me, in this case, algebraic geometry means, for Hurwitz numbers, it means always the moduli space of curves. And here you have several things, like you have the string equation, you have the dilaton equation, you have some closed formula in genus 0 and 1, and you have other things. And then for the computer side, there is, if you access Cocalc, there is a beautiful package that was developed by Vincent Delacroix, which is here, together with Jason von Zelm and Johannes Schmidt, that is called ADM cycles. And I use it a lot. I like it a lot. And it's very easy. Tomorrow I will state just, I will write down a few lines of code that you can just type on ADM cycles. You use it on the browser, you don't need to install anything, you just go online and type and compute. So it's very, very nice. Okay. So let's go with Hurwitz numbers now. So of course you have two approaches for this. You can either go with algebraic curves, or you can go with Riemann surfaces. We will be using this one. But for some exercises, some proofs, this one it's handier, but generally it would be Riemann surfaces. Yeah, so let me recall some very basic facts that will bore you. What should I actually recall? Yeah, I should recall this. So the picture is the following. You have a Riemann surface, and then you want to study a map to another Riemann surface. And then, okay, here you have your atlas with your charts. You have C here, and you have C here. You take a point X, and you have this map F. So you look at here, you'll have some point F of X. And then you have your transition maps. And then you declare that the map is holomorphic at the point X, whenever you can just take the inverse of that, go down, go here, and this is holomorphic. And then you define the same thing in a neighborhood of every point, and then you say that the map is holomorphic if it's holomorphic near any point. But the non-trivial thing is that locally, around x, f behaves like that. Z goes to some number here. And this number, I want to define this number E of x. And this number is an integer. Yeah. Exactly. I'm just stating that you have, so here, this map locally looks like z goes to z to the power, say, 5 or so. And near every point, you can find such an expression. You have a well-defined exponent. That's what I'm saying. Okay. I want to call this local normal form. It's not a form in the sense of dz, it's the form that it takes. Okay. And I want to call this Ex the ramification index. And so if Ex is equal to 1, then I want to say that x is unramified. If Ex is equal to 2, I want to say that x is simply ramified, so it's a simple ramification. And if E of x is 2 or more, then I want to say that x is a ramification point. And I will call f of these ramification points, I want to call them branch points. And I want to call the locus of all branch points, I want to call it B. B for branch points. And I want to call R the set of ramification points. Let me write all ramification points. Okay, I think you probably all heard this at some point, but maybe it's not exactly what you do, so. Yeah, so there is a fact, that is that the cardinality of B is finite, and the cardinality of R is finite, because we're dealing with holomorphic maps. So we are happy, because now we can list them. Okay. Also, there is another fact. That is that if you take a generic point downstairs, let me call this x, and I will call this y. So x is the domain, and y is the codomain. And if you take a generic point downstairs, y, now if you look at f per image of y, if you look at the cardinality, this is constant generically. Okay, let me write it like that. If you take generic y1 and y2, then the cardinality of the fibers is the same. okay? Oh, I'm just saying something very easy. Take a point downstairs. Look at the fiber. The cardinality is the same, except for very few points, which are finitely many. We call this the degree of F. So now you can see the picture is a little bit like that. The picture is a little bit like that. You have some surface upstairs, and this is my x, and I have some genus. Okay? And downstairs I also have some genus. This is my y. And I want to look at maps F, which are holomorphic between two Riemann surfaces. And then if I collect these facts together, what I get is that, can I write with blue? Or you will kill me. If I take a point here that I call y, like generic, and if I look at a little disk around this point, when I lift it upstairs, I will find a certain number of disks. Okay? So this is what happens generically. I take a point, I take a neighborhood and I lift it, and let's say that we have, let's call this degree D. But then I have finitely many points all around, say that one is here, one is here, one is here, and I fix them. And then when I look upstairs at these special points, so these are the points of B, and if I take the per image, I will find R. Not exactly R. So it's true that if you push down the ramification points, you will find branch points, but it's not true the vice versa, because what can happen is that if you lift these points, you can find here a point in which, say, if you have a neighborhood here, maybe here you'll have like something interesting happens. So say 3 sheets of the cover, they get mixed there, they get crunched. So locally this map over here is, so here you will find z goes to z to the power 3, right? And then if you do it here, you'll find maybe z goes to z to the power 5. And then here you will have another per image, but this maybe it's not ramified. This is maybe z goes to z to the power 1, so it's not ramified. And then you look at the other per images, and here is 17. It doesn't matter. The point is that you have finitely many of them, of these special points. And for each of them, you look what happens upstairs. But what you know is that even if here you will get some mess of these sheets that collide together, if you take the sum of all these exponents over here, you should be getting the degree D, right? You have D sheets, and you have to deal with them. And you can compose them, you can shrink them, but you have D. So at the end, if you take 17 plus 1 plus 1 plus 5 plus 3, it should be D. There's nothing to do about it. So at the end of the day, your data is just a bunch of partitions. So you can build the combinatorial data. It is like that. You take a B, and this is, say, P1, Pm. And then each of them will give you a partition. Let me call it eta 1, eta m. So these are all partitions of the same D. So for example, if this point here was P1, and to P1 I associated the partition eta 1, that is, so let me say that this was z goes to z to the power 1. Now this partition would have been 17, 5, 1, 1, there's a 3. That's very easy. It's very easy. Just have finitely many points. You look upstairs, you find something. That something is your partition. You collect them all. And this is your combinatorial data. But then there is a special theorem. Then there is a theorem. Sorry? The eta is the partition that is given by these exponents over here. Okay. So, for example, this was 17, 3. This one was 3. Z goes to z to the power 3. I had 17, 1, 1, 5, and 3, and I just reordered them into this list. But then I know that this should be a partition of D, not of any number. But then there is a theorem. And it's a little bit magical. So here you have holomorphic functions of Riemann surfaces. And you have to fix stuff. You have to fix the genus upstairs, the genus downstairs, the branch points, and so on. So you have to fix many of these ingredients. But let me say this way first. Every time you have such map, F, you can extract these partitions. I take F, I take the branch points downstairs, I look at what happens upstairs, I look at the exponents, I know that I can find each of them, because this is local normal form. I take all the coefficients, all these exponents, and I put them in the list. Then I go to the second point, P2. I look upstairs, there will be another partition. Then I look at P3, up to Pm, and I collect all of them. So at the end, I have just M partitions. So what I'm saying that here you have partitions. And this is possible because of this local normal form. But there is a theorem that goes in the opposite direction. So this Riemann existence it tells you that somehow this, the way these ramifications are arranged define F. And so now you're very happy, right? Because we started with something like geometrical, which was in principle very hard to handle. Like I wouldn't know how to deal with this for high genus, high ramifications, and so on. It's very complicated. But now we have a recipe to associate something combinatorial to it. And now we can do computations. So we took a geometric problem, and now it's a combinatorial problem to some extent. Yeah.
So on the right-hand side, the datum is a D and a finite amount of partitions of D.
Yeah, so I have to specify many things, right, to get this bijection. Right. I have to fix the genus upstairs, the genus downstairs, the degree of the map, the points downstairs. And then here you will have partitions of the degree. So here you will have M partitions of D.
Right.
To make it more precise.
So you fix G, H, and the number of points downstairs.
Yeah.
That gives you...
Yeah, so the genus upstairs, let's call it G. It's the genus upstairs, and the genus downstairs is H.
Yeah,
But I want to fix G and H. And also the branch B.
Yeah.
The branch, maybe it's enough. Maybe it's enough. You had the same question. Okay. Yeah. Thanks. I didn't want to make it precise, but you forced me to, which is good.
And the relation between G and H and B, there is a relation.
Yes.
Okay.
You're one of these students that already studied next.
So, can two different branch points be associated to the same partition? So, can the same partition appear twice?
Yes, of
Okay.
course. Yeah. You don't have one partition does not constrain the other ones.
Okay.
I mean, it does, but in a very mild way. That's what he was suggesting. Like, is there a relation between the genus upstairs, the genus downstairs, and how packed the partitions are? Yes, there is exactly one relation. And so it's true that if you change one partition, you force some other partition to change. But it's not a very hard constraint. Just all together, all the partitions and the Geneva should satisfy a single equation. Yes. Maybe it's actually now, this thing. Yes. It's just the next page. Great. Maybe I keep this drawing. Maybe I keep this drawing. Right here. So these constraints basically ensures that the Riemann surfaces are compact, that we can close them up. And the constraint is the following. You take a 2 minus twice the genus upstairs, and this is equal to 2 minus twice the genus downstairs times the degree, and then you have to subtract sum over all x, and here some ex minus 1. And now you can get very angry, because I wrote the sum over points of a Riemann surface. And this is all x in x. Yeah. But every point has ex equal to 1, so this vanishes, except finitely many. So this is a finite sum. Yeah, so the proof, it's beautiful. And it's just the following. This one here is just the Euler characteristic, right, of x. And this one here is the Euler characteristic of y. Oh, it's written here, but there's a mess. H is the genus downstairs. And G is the genus upstairs. So now I'm saying the following, that Euler characteristics upstairs is equal to Euler characteristic downstairs times the degree with a little bit of defect. How do you prove this? Take a graph. You take a graph downstairs, so you lift it upstairs. Exactly.
Well, do it, please.
No, it's an exercise. No, okay, I do it fine. So just take a graph downstairs that passes through all these points, and such that you have faces. So you have, every time you have a genus, you have to break this, so that the faces are disks. So now it's Hilbert's course. So you take a good graph, what is called good graph, of on Y. Is it Y? Yes, on Y. Let me call it gamma Y. Okay, and now what happens? You take f per image of gamma Y, and you call this gamma X. Okay, now there's just one little algebraic manipulation, but the proof, I mean, you will be able just to write it down straightforwardly, right? Because we just said that they are all partitions of D. Every time we have a mess here, we have many sheets that come together. If I sum up all these interesting points, actually, so where things happen, if I sum up all these exponents, it should be D. So if you have any, say, B in B, and then you look at F per image of B. Sorry, I don't want to write it like that. I want to write that if you take the sum over all points X in X, such that not in X, but in the pre-image of B by F, and if I take the sum of EX, this is D. That's exactly what we've been saying so far. It's exactly, like if I take the sum of all the exponents, that's D. We're convinced about this. So now let me do the small algebraic manipulation. I want to write now that the sum of the same thing, X is in the pre-image, B. But now I want to write E x minus 1, right? I want to write this because I want to prove this formula. So if I write minus 1, I have to write plus 1. But if I write plus 1, I can bring it outside of the sum, and instead of writing plus 1, I can write plus the cardinality of this. Yes, this is an epic moment, so we need some epic music. Okay, so now the cardinality of the pre-image, now it's not a generic point anymore. This is in B. So this is not D. This is actually D minus a defect. And this is the defect. Right? This equation tells you that the more you mess up the sheets, the more defect you'll have. This equation tells you that every time you have a special point, you need to subtract 1. So if you have fewer, it will get messier. If you distribute a partition, say partition 2, 2, 2, 2, 2, you'll have to pay more. But if you contract all the sheets together, say this is 17 plus 5 plus 3 plus 1 plus 1 is 28. If you have just a single point with 28, then you'll have a defect of 27, which is the highest possible. Okay, and now you just do the Euler characteristic of the graph. Maybe I should do it just for the satisfaction of having the proof written down. If you take the cardinality of X is equal to write the vertex of gamma X minus the edges of gamma X plus the faces of gamma X. And now this is equal to D times the vertices of gamma Y, right? Because every time I have a vertex upstairs, I can lift it, but then I have to pay the price. How much do I have to pay? This is how much I have to pay. So I have to add it minus the sum over all f of the vertices v for all v, ex minus 1. Okay, let me write this. And then minus d times e, comma y, plus d times faces. So I'm claiming the following. We know that every time we draw a graph and we compute vertices minus edges plus faces, we're going to get the Euler characteristic, right? And now we just want to take each of these ingredients one by one, lift them upstairs, and see what happens. And what happens is that if you take the vertices, you will get deeper images minus the defect, and with the other two, nothing interesting will happen. So now you can repack. You can repack these, and these together, and you will get d times the Euler characteristic of your y minus some x in x. So that's proved. So you have three things. This is good. This is good. Here you have some defect. This is the defect. And this is what you carry on in the computations. OK.
And sorry, and good means that the complement is a union of disks, right? Is that the only requirement? Yeah. Okay.
OK. Now we can define Hurwitz numbers. What time is it? Say. OK. So assume that the genus downstairs is 0. Assume age equal to 0. So you have now upstairs you have some genus, and downstairs you have P1. You have infinity, 0, and some branch points, B, like that. And then finally, we can define Hurwitz numbers. Yeah, maybe I didn't have to prove Riemann Hurwitz, but it was fun. We will do a little bit less. OK, so age, depending on the genus G, and also all these partitions eta 1, eta m. Yeah, this is defined to be the sum over all f, 1 over the automorphism of f. And I have to explain two things here. But this is what I want to do. I want to define Hurwitz numbers that depend on the genus upstairs and also on all these partitions of D, right? I don't have to write D because I just point at any of these and look at the size of the partition. So you don't have to remember it. This is defined to be the sum over all holomorphic map of genus G with these ramifications. And then you take 1 over the automorphism of F. So I have to say what the automorphisms are and what the classes are. And I claim that these numbers are in Q. Well, actually, this is obvious once, yeah. Actually, you have to prove two things, that this sum is finite and the automorphisms are finite. But this is, again, more or less obvious because if the Euler characteristic is negative, then you have finitely many automorphisms. And again, here, this sum over F only depends on the partitions, and for each partition you have to decide how you mix up these sheets that come together, and because there are finitely many sheets, there are only finitely many ways to mix them up. So,
So each eta is a partition, right?
yeah, yeah. So the only thing that I have to write is that F1 that goes from 1 to P1 is the same, is equivalent to F2 if and only if there exists some phi from x1 to x2 such that F2 composed with phi is F1, and this is isomorphism of Riemann surfaces. So this is the definition of classes. Okay. So how to count them? Yeah.
Ramification points, they are not labeled, are they?
No.
Okay.
They are not labeled. Actually, you will see that there are two conventions. Either they are labeled or not. And in fact, it's almost the same thing, counting the labeled ones and counting the unlabeled ones. The only thing that you need to remember is to multiply by the automorphism of the partition. So you take the product of all automorphisms, of the cardinality of all automorphisms of all partitions. So it's the same amount of information, that's what I'm saying. Okay, so you can try geometrically. I wouldn't recommend it. Because it's very hard. I mean, you have to check that you're counting all the Fs, and then for each of them you have to compute the automorphisms. You can do it when the genus is very low and the ramifications are very simple, and then it gets very complicated very quickly. So we can actually do it with a group algebra. So the idea is the following. Now the genus downstairs is 0, so you have a sphere. Now you have a sphere. It's much simpler. I'm interested in representations from the fundamental group of P1 minus B to the symmetric group, SD. This is what I want to do. This is what I want to do. And I want to do something very simple, in fact. Take any point downstairs. Okay, so I'm saying that if you want to actually count Hurwitz numbers, F by F, it's hard. Let's do something more combinatorial. I want to use the group algebra. And now I'm going to say how it is possible to do this. The idea is to consider representations from the fundamental group of P1 minus finitely many points to the symmetric group. Yeah, it's like, yeah, group algebra, I will use Q of ST. So let's take an unramified point, Y. So that's a generic point. Let's make loops now. I want to take a loop around P1. This will pick up some monodromy upstairs. Then I go around P2. Again, this will pick up some monodromy. And I keep going this way. I make my flower until PM. And just take loops around all points. And there are finitely many, so there are no problems. And then, after I'm done, I realize that, okay, but this is a fundamental group, so you can compose loops and then get just one big loop around everything, right? But what if you have a big loop around everything and you're on the sphere? So then you can just take your rope and put it around the sphere, right? If you went already around all holes, one by one, and all of a sudden you put it around the sphere. So it contracts to a point. Which means basically that if you take the products of all the monodromies, that should be trivial. So somehow I know that product of all monodromies is trivial. Should be trivial. Naively. Okay, so now I want to define this element, C alphas. Alpha is a partition of D. They're all partitions of D.
Sorry. How do I know that there exists a representation in the symmetric group?
I'm not claiming anything. I'm just saying that I take a generic point and I take a loop around a branch point. Yes. Then you look at the map upstairs. Yes. And this will pick up basically how the sheets mix. So, for example, like here, if you look at the preimage of Y, you will find the D preimages. Just choose one. You will be on this sheet over here. Now you go around the loop, and then you will end up on another sheet. So you start. These sheets are labeled from 1 to D. So you start from 1, you go to the 5th. So you have a permutation that whose cycle is 1, 5, 3, 2.
So you take the preimage by F of your loop,
yeah,
and the endpoints are permutation of the initial points. Yeah.
Okay, we also know, so let me define the C alpha. You start from a partition of D, and now you define the sum of all sigma in SD, such that the cycle type of sigma is alpha. So what do I mean? Let me recall what do I mean by cycle type. If you take a permutation that is 5, 3, 1, 2, 7, 6, and 4, then the cycle type is just given by, is the partition that is given by the length. So you just take this length. So this will give the partition 4, 2, 1, which is a partition of 7. And in fact, this lives in S7. So every time you have a permutation, you can associate a partition. And this is a conjugacy, the conjugacy class. And now, what I'm doing is exactly that. So C alpha is the formal sum with coefficient 1 of all the sigmas that have the cycle type alpha. And this lives in the group algebra of SD. And now I want to convince you that Hurwitz numbers can be counted this way. And in fact, the theorem is that
So this set of generators are the center of the group.
yeah. And then the hg, eta 1, eta t, they are equal to 1 over d factorial. And then you do the following. You take the product of all the c eta I from 1 to m. And then here, what do you need to do? So let's think a little bit. Inside this c eta I, there are all the possible ways to fill that partition with the permutation with that cycle type. So I consider the formal sum of all possibilities, and I'm taking the product of all of them. But at the end, when I'm done, I can pull it on the other side of the sphere, and that should be trivial. So that should be the identity. So I should be counting how many times the identity I have. So let me write here C identity as an operator that applies to this product and counts how many times you get the identity. So by this symbol, I mean that x to the power 5 inside an xn is equal to a5.
Is this called the Frobenius formula?
You're extracting the coefficient of the...
Yeah. So by these brackets, I mean the operator that extracts the coefficient. So x to the power 5 in brackets applied to my power series is a5. Yeah.
M, not on T.
It should depend on.
On M.
Thank you.
So
Yes. And then you can complain in many ways. Okay, let's call this Frobenius formula. Although I usually call, not just me, but some people, Frobenius formula. Usually call Frobenius formula the next one. So you take this formula, you do like a further restatement,
Hello?
and that's what people refer to Frobenius formula.
Danilo.
Yeah.
You have on the left-hand side, on the first term, you have on the right, CID. No, why do you have?
C eta I.
And then before that?
Product identity.
Identity. Oh,
Identity.
God. Thank you.
And then, okay, you can complain more than that. Yes, another complaint, please. Yes, that's another good complaint. And there is also another good complaint, that is that this one does not depend on the gene, right, in principle. Here I see G, and here I don't see G. Yeah, exactly. So here, G is determined by a Riemann-Hurwitz formula. So I don't have to write it. So suppose that you don't know G. You can just compute it because you know the eta is. So this is completely determined by the partitions. If you remember, the formula was 2 minus 2G is equal to 2 minus 2H, which is now 0, by the way, times D, plus the EX minus 1, right? But OK, so which means that now this is 0. The D, we can extract it from the partitions, so I don't need to write it. And these guys are completely determined by the etas. So the etas exactly carry this information, and as you see that now the genus is expressed by this single equation in terms of the other ingredients. It's stronger than me. Yeah? Alpha. No, take any partition. So this is my definition of C alphas. Just take any partition and define C alpha this way.
So what's CID?
Yeah, okay, let me make an example. But so just to be sure. Take any partition and define C alpha. Now, how do you want to use these C alphas? You plug the eta i's inside. You take the product of all of them, and you count how many times you have the identity. So what you're doing is taking this branch point over here, you go with a loop around this, and then you picked up some sigma that is of cycle type, that is one of the summons of eta 1. Let me write it. The first time you go around P1, so around P1, you pick up some sigma of cycle type eta 1. So sum over all of them, all such sigmas. If you want to count every map, you need to sum over all sigmas that you can pick up by doing this loop. If you want to count all f's, and such that the cycle type is given by the partition over here. Does that make sense? And after you're done with all the points, you put it on the other side, you get nothing. So which means that at the end of the day, you should be getting the identity. Let me make an example.
I'm not sure if this will be super helpful, but what you just described gives a representation of the symmetric group, and you're computing the trace there, right?
Yeah.
So
exactly.
that's what you're saying.
Yeah.
Okay.
And the D in the formula is the D that you had in the...
Yeah, it's always the same D. It's the degree of the cover.
And is there any relation between the number of the D that you have and this parameter alpha? No.
Yeah, so all the eta i's are partitions of D, and this is true for any I, from 1 to m.
Yes. Thank you.
Yes?
Determine the square brackets because saying you take the coefficient.
Yeah, okay. If you want, yes.
The identity in
some
SD.
people write it like that, but okay.
Yeah.
Identity. Yeah. Let me make an example. I want D to be equal, to be 3, okay? And I want C3 times C3. So what is C3? Okay, I want to count how many times the identity is there. Identity, C3, C3. This is equal to identity, and here you have 1, 2, 3 plus 1, 3, 2. One, 2, 3 plus 1, 3, 2. How many times do you have the identity? Yeah. So if I take this guy times this guy, that's okay. That gives me 1, right? And if I take this guy times this guy, I also get the identity because they are just like inverse of each other. But if I take the mixed ones, if I take this one and this one, no, I don't get the identity. And if I take this one times this one, no. So I have 2 answer.
When you say times, you mean composition of permutations.
Yes. You're convinced, right? 1, 2, 3 composed with 1, 2, 3 is 1, 3, 2. But 1, 2, 3 composed with 1, 3, 2 is the identity.
And divided by 2 factors.
Divided by?
You had here 1 over D factor.
Yeah, so that would be 3 factorial, right? So that will give me 1 over 3 factorial. So this would be 3 factorial. So the final answer would be 1 over 3. And then you need to check that this is actually Hurwitz numbers. So it satisfies Riemann-Hurwitz formula. Because now I just put some C's there. But if you put random C, it's not necessarily Hurwitz number. You should check Riemann-Hurwitz is satisfied. And that's the only thing you need to check.
I'm still not sure what the automorphism was when you first wrote the formula. So now I know how to compute these, but you had the first expression you gave was like 1 over automorphism of F.
Yeah.
What was that automorphism?
So to compute with this formula, you don't have to worry about it.
Yes.
Because
But
it's
what
not there
was-
anymore.
yes.
But if you want to compute a geometric formula, I gave the definition of how when two maps are in the same conjugacy class,
Yeah.
in this equivalence class. So you count how many, the cardinality of that, count how many symmetries that F has, how many maps are isomorphic to that.
Okay. I see. Okay. Thank you.
Okay, cool. What's the time? Okay, we're almost at the 1/4 of the session. But some people say that less is more, so maybe we should do just a few things, but hopefully there will be. Yeah, but it's also not good to do more if people are tired, because it would be not absorbed. Yeah, thank you for resisting so much. I would be asleep already. So what shall we do in 10, 20 minutes? I think I should answer your question at least. You were like, yes, of course you should answer my question. Yes, what about connected and disconnected? So I'm cheating just a little bit, because it can happen that the surface upstairs is not connected. And then we need to remember this. So there are two enumerative problems. Either we count connected Hurwitz numbers, in which we require the surface upstairs to be connected, or possibly disconnected Hurwitz numbers. These ones over here are the possibly disconnected Hurwitz numbers, and I indicate that with a bullet. Let me write it. So these ones are possibly disconnected. Domains X. So the surface upstairs. The surface downstairs is always P1, so there is no ambiguity about it. And H, a circle like that is connected. This notation was, I think, initially used by Pandaripande or Kunkov, do you know? I think it was their paper. I don't know of any paper before that. So this is the theorem for possibly disconnected ones. And now you can ask, how do you count connected? And the theorem for, say, the formula for the connected ones, connected, is the following. H connected, G eta 1 eta m, is equal to the same thing, identity. But I put a bullet circle here. I need to explain what it is. And then you just take the product, 1 to m, c eta I, where this guy now, it's a little bit tricky. This one here, now it counts so identity bullet counts how many 2 plus sigma 1 sigma m such that This should be of cycle type eta 1, of course, and this should be of cycle type eta m. As always, such that sigma 1 composed blah, 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 composed sigma m is the identity, right? And moreover, if you take all of them that span a transitive subgroup of SD. Transitive. Which means the following. So imagine we are all these people in the room, and now we start shuffling, like changing places, and these sigma i's are permutations of us. You don't want anyone that stays alone. So you want to count these tupulas, and only that. Each of these will contribute 1. But you only want to count the ones in which nobody stays still on the table. And this guarantees, from the point of view of the cover, it guarantees that if you have something like that, I'm coming to the question, sorry. If your x is that, this is x, the whole of it, you have some genus upstairs, some genus downstairs, and maybe there are just a few sheets here. Maybe here is like just 2 sheets, and here there are 17 sheets. If at least once you collide a sheet that is here and a sheet that is here in a ramification point, then you're sure that it's connected with that. So if it's transitive, it means that every sheet gets mixed with the other ones at least once, and therefore you kind of glue them. So there's no chance that they are independent. They get connected, all of them. Yes?
The idea with a bullet, a circle on top of it, it's not defined on the group algebra, is it? It's defined on some kind of product, right?
Yeah.
Oh, okay.
I mean, for me, it is defined like that. You need to actually count how many tupulas with these properties you have. I think this is a well-defined thingy. You count them. You count the tupulas one by one.
It's not defined because you're taking a logarithm.
Sorry?
You're like taking a logarithm. So
Yeah.
that's why it ruins your origin.
I'm definitely taking a log, and yeah, it's not defined, but like that it is. You have finitely many tupulas, just counting something combinatorial.
Yeah, sure. I'm just saying that this
yeah, it's not
function
defined in
is
the group algebra. Yes, it's a trick. Like I'm writing it in a compact form.
Okay. Okay.
But what actually means is that you count how many tupulas you have. So it's a mess. You have to like manually go by one by one, or you just teach a code to do it for you, because otherwise it's really long. Okay. Please. How do I multiply? Okay. So if you have an element that is 5 times 1, 2, 3, plus 17. 1, 2, 3, 1, 2, 3. So 1 goes to 2, 2 goes to 3. So 1 goes to 3. Yeah, from here, 1 goes to 2, and then you look at the next one, 2 goes to 3. So at the end of the day, 1 goes to 3, which is what happens here. Now 2 goes to 3, and 3 goes back to 1. So 2 goes to 1, that's okay. And now I need to check just the third one. 3 goes to 1, and 1 goes to 2. So at the end of the day, 3 must go to 2, and that's the case. Okay, and if you have at the same time permutations and numbers, you just multiply. So say that you have something like that, 1, 2, 3. You just do like the most obvious thing. You take this times that, and you remember the coefficient, plus this times that, and you remember the coefficient. So this would be 5 times 132 plus 17 times what? 1 goes to 2, 2 goes to 3. So maybe it's 1, 3, right? 2 goes to 1, 1 goes to 2, 3. I think it's that. So maybe I should make more examples. Say that if D is 3, then C 2, 1 is 1, 2 plus 2, 3 plus 1, 3. In general, if you take any D, then C2, 1, 1, 1, 1, 1, 1, 1, like whatever you need. You just complete it with ones. That's just the sum of transpositions. Right? Basically you take the sum over all elements that mix 2 sheets, and that's just, for any D, is the sum of the transpositions. And if you take, say, C, and here you have the partition D, that's just the sum of all 1 cycles. Does make sense? And so now you can define simple Hurwitz numbers. You can define simple Hurwitz numbers.
What do you mean by 1 cycle?
Sorry?
What do you mean by 1 cycle?
Just 1 cycle.
I would call that a 7 cycle.
Yes.
This is 1 cycle of length 7, but there is only 1 cycle.
Okay. If you want, I can write sum of all single cycles, individual cycles. How do you want me to call it? Yeah? Just everything is inside 1 cycle. So simple Hurwitz numbers are like that. Basically, what you want is genus G, and here you have this eta 1, and that's it. Basically, you just want eta 1. You just eta 1. And that would be absurd, I mean, to just consider eta 1 and nothing else, because the Riemann-Hurwitz formula would not work for every genus. You cannot have simple Hurwitz numbers with 1 ramification and every genus that you want. So you need to allow some freedom in the ramifications, but you want all other ramifications to be simple. So if you remember, we were saying that if Ex is equal to 2, then X is a simple ramification, right? So simple Hurwitz numbers are with just 1 non-trivial partition, and all the other ones are simple ramifications. All others are simple. That's what I call simple. So now I can just write age, say disconnected, because then it's easier, G, and then I just have to write eta. I don't have to write eta 1, eta m. It's just one eta. This is 1 over d factorial, count the identity, inside c eta, times c2, 1, 1, 1, 1, 1, 1, 1, 1, 1. This is d minus 2 times, to the power b. So these are just simple Hurwitz numbers. Now you can complain again. What is b? Exactly, that's exactly the complaint. So, what is b? It must be given by Riemann-Hurwitz formula. It must be. So Riemann-Hurwitz formula is 2 minus 2g equal to 2 times the degree, because the genus is 0, minus sum over ex minus 1, x in x. Okay, but now let's think. There is just one single ramification that is doing something interesting, and all the other ones are mild. Yeah? Yes. Let me do this. So one thing at a time. But thanks. Yes?
Why is it not b minus 1 instead of b? Because I thought that you have b of then one of them is eta. So the rest are, so we will be left with b minus 1 for which you have.
Yeah. So now I'm doing simple Hurwitz numbers. The definition of simple Hurwitz numbers is that there is just one partition that does something, and all the other partitions are simple, which means that
but you have b minus 1 of those, right? You have
No.
b minus 1 of the rest
I
of
have
them?
b of them.
Oh,
I'm
I see.
defining b to be
Oh,
the
I
number
see.
of them.
Okay, thank you.
Yeah. So this is, if you wanted, this is the definition of b. And then b is determined by Riemann-Hurwitz. Yeah. So they are just two sheets that come together, and therefore they can be represented by a transposition. So I need the sum of all transpositions, which is C2. So I just take C2 from here, I plug it here, and I take it sum of them. Now I want to compute how many? Compute how many? Simple ramifications. Okay, so 2 minus 2g is equal to twice the degree minus the defect. But now let me split it. What is this defect? It's either I take stuff from my eta, or I take stuff from the simple ones. So I can split the sum. I can write that this is minus the sum of eta I minus 1. I from 1 to the length of eta, and then minus the sum of 2 minus 1, right? Because E of x is 2 for all the other ramification points, and I have b of them. So now 2 minus 2g is equal to 2 times d minus I take this minus 1 outside, so that becomes plus the length of mu. And then I have minus the sum of the eta i's. But we know that the sum of the eta i's is always d.
This is the length of eta.
Sorry?
Length of eta.
Thanks. I'm so used to call it mu. And then it's minus, okay, 2 minus 1 is 1, and we have b of them. So it would be minus b. So now you have minus d and d, they go away together. So you can cross the 2 and that. And so now b is equal to 2g minus 2 plus the degree plus the length of eta. And that's it. I think this is a good time to stop.